So in the last lecture, we looked at how to make iterative or inductive definitions more efficient than naive recursion. And we saw memoization and dynamic programming as tools to do this. So now let's look at a typical problem and see how we can apply this technique. So here is a problem of grid paths. So we have a grid here. You can imagine there are roads which are arranged in a rectangular format. And we can imagine that the intersections are numbered. So we have 0, 0 at the bottom left corner. And in this case, we have 5, 10 because we have going across from left to right, we have 1, 2, 3, 4, 5 different intersections and 10 going up. So we have at 5, 10, the top right corner. So if these are roads, the constraint that we have is that one can only travel up or right. So you can go up a road or you can go right, but you cannot come down, right? So this is not allowed. So these are one-way roads which go up and right. And what we want to ask is how many ways there are to go from the bottom left corner to the top right corner. So we want to count the number of what are called grid paths. So a grid path is one which follows this, right? So we want to know how many such different paths are there which take us from 0, 0 to 5, 10 only going up or right. So here is one path drawn in blue. Here is a different path drawn in red, and notice that these two paths actually start in different directions from the first point and they never meet except at the target. So they don't overlap at all. On the other hand, we could have paths which overlap. So this yellow path overlaps for part of its way with the blue path in this section, and it also overlaps with the red path in two portions. Right? So there are many different ways in which we can choose to make these up and right moves, and the question is how many total such different paths are there. So there is a very standard and elegant combinatorial solution to it. So one way of thinking about this is just to determine how many moves we have to make. We have to go from 0 to 5 in one direction and 0 to 10 in the other direction. So we have to make a total number of 5 horizontal moves and 10 vertical moves. In other words, every path, no matter which direction we started in and which choice of moves we must make 15 steps. And of these, 5 must be horizontal steps and 10 must be vertical steps because they all take us from 0, 0 to 5, 10. So all we have to do, since we know that these 5 steps are horizontal and 10 are vertical, is to just demarcate which ones are horizontal, which are vertical. Now once we know which ones are horizontal, we know what sequence they come in, because the first horizontal step takes us from column 0 to column 1. The second one takes us from 1 to 2. So we can't do it in any order other than that. Right? So we have, in other words, we have 15 slots where we can make moves, and then we just say, okay, first we make an up move, then we make a right move, then we make an up move, then make another up move, and so on. So every path can be drawn out like this as 10 up moves and 5 right moves, and if we fix the 5 right moves, then automatically all the remaining slots must be 10 up moves, or conversely. Right? So it's either 15 choose 5, which is the way of choosing 5 positions to make the right move out of the 15, and it turns out that the definition of 15 choose 5 is clearly the same as 15 choose 10, because we could also fix the 10 up moves, and the definition is basically, if you know the definitions, n choose k is n factorial upon k factorial into n minus k factorial. Right? So this k and n minus k basically says that 15 minus 5 is 10, so we get a symmetric function in terms of k and n minus k. So in this case, we can apply this formula, if you would like to call it that, and directly get that the answer is 3003. So there doesn't appear to be much to compute other than writing out large factorials and then seeing what the number comes. But the problem becomes more interesting if we constrain it by saying that some of these intersections are blocked. For instance, supposing there is some road work going on and we cannot go through this intersection 2, 4. Right? So this is the intersection 2, 4, the second column, and the fourth row counting from below. Right? It's actually 2, 3, but 1, 2, 3, 4. Yeah, 2, 4. So now, if we can't go through this, then any path which goes through this particular blocked intersection should no longer be counted. Out of those 3003, some paths are no longer valid paths. For instance, in the earlier thing, the blue path that we had drawn actually goes through this. Okay, the red path does not. But the yellow path overlapped with the blue path, unfortunately, in this bad section, so it also passed through this. So there are some paths which are allowed from the 3003 and some which are not. So how do we determine how many paths survive this kind of block? So again, we can use a combinatorial argument. In order to be blocked, a path must go to 2, 4 and then from 2, 4 to 5, 5. So if we could only count how many paths go from 0, 0 to 2, 4 and then how many paths go from 2, 4 to 5, 10, these are all the bad paths. So we can count these bad paths and subtract them from the good paths. How do we count the bad paths? Well, we can just solve a smaller version of the problem. So we have an intermediate target. So we solve this grid. How many paths go from here to here? How many paths go from here to here? Right? So from 0, 0 to 2, 4, we get 4 plus 2. Remember, it's 10 plus 5. It was at the target. So 4 plus 2, choose 2. So we get 15. And from here to here, the difference is that we have to do in both directions 3 and so we have to go up 6 and we have to go right 3, right? We are at 2, 4. So we have to go from 4 to 10 and from 2 to 5. So we have 6 plus 3, choose 3, 84 ways of going from 2, 4 to this. And each of the ways in the bottom can be combined with the way on the top. So we multiply this and we get 1260 paths which pass through this bad intersection. We subtract this from the original number 3003 and we get 1743 paths which remain. So our combinatorial approach still works. Now what happens if we put two such intersections? Okay, so we can do the same thing. We can count all the paths which get blocked because of the first intersection. We can count all the paths which pass through. In this case, 4, 4 is the second intersection which has been blocked. So we can count all these paths which pass through 4, 4. So this we know how to do. We just computed it for 2, 4. But the problem is that there are some paths like the yellow path which pass through both 2, 4 and 4, 4. So we need a third count. We need to count paths which pass through both of these and make sure we don't double count them. Okay? So one way is that we just add these back. So this is something which is called in combinatorics inclusion and exclusion. So when we have these overlapping exclusions, then we have to count the overlaps and include them back. And we have to keep doing this step by step. So if we have 3 holes, we get an even more complicated inclusion-exclusion formula. And it rapidly becomes very complicated even to calculate the formula that we need to get. So is there a simpler way to do this? So let us look at the inductive structure of the problem. Suppose we say we want to get in one step to a intersection I, j. How can we reach this in one step? Since our roads only go left to right and bottom to top, the only way we can reach ij is by taking a right edge from its left neighbor. So we can go from I minus 1j to ij, or we can go from below from ij minus 1 to ij. Notice that if a path comes from the left, it must be different from a path that comes from below. So every path that comes from the left is different from every path that comes from below. So we can just add these up. Right? So in other words, if we say that paths ij is the quantity we want to compute, we want to count the number of paths from 0, 0 to ij. These paths must break up into two disjoint sets, those which come from the left, which recursively or inductively, if you prefer to say, is exactly the quantity paths I minus 1j. How many paths are there which reach I minus 1j? Every one of these paths can be extended by right edge to reach ij, and they will all be different. Similarly, paths I, j minus 1 are all those paths which come from below, because they all reach the point just below ij, and from there each of them can be extended in a unique way to ij. So this gives us our simple inductive formula. Paths ij is just the sum paths I minus 1j, paths ij minus 1. Then we need to, of course, investigate the base cases. In this case, the real base case is just path 0, 0. How many ways can I go from 0, 0 and just stay in 0, 0? Well, there is only one way. It is tempting to say 0 ways, but it's not 0 ways, it's one way. Otherwise, nothing will happen. Right? So we have one way by just doing nothing to stay in 0, 0. And if we are now moving along the left column, right? If we're moving along the left column, then there is no paths coming from its left because we are already on the leftmost column. So all the paths from to 0j must be extensions of paths which have come from below to 0j minus 1. Similarly, if we are in the bottom row, there is no way to come from below because we are already on the lowest set of roads. So paths I0 can only come from the left, from paths I minus 1, 0. So this gives us a direct way to actually compute this even with holes. Because the only difference now is that if there is a hole, we just declare that no paths can reach that place. So we just add an extra clause which says paths ij is 0 if there is a hole at ij. Otherwise, we use exactly the same inductive formulation. And now what happens is if I have a hole below me, no paths can come from that direction because by definition, paths of ij at that point is 0. So once again, if we now apply this and do this using the standard translation from the inductive definition to a recursive program, we will find that we will wastefully recompute the same quantity multiple times. For instance, paths 5, 10, okay, so if you have paths 5, 10, it will require me to compute this and this. Right? These are the two sub-problems for paths 5, 10, namely 4, 10 and 5, 9. But in turn, in order to compute 4, 10, I will have to compute whatever is to its left and below it. And in order to compute 5, 9, I will also have to compute what is to its left and below it. And now what we find is that this quantity, okay, namely 4, 9, is computed twice. Once because of the left neighbor of 5, 10 and once because of the neighbor below 5, 10. So as we saw before, we could use memoization to make sure that we never compute ij twice by storing a table I comma j, and every time we compute a new value for I comma j, we store it in the table, and every time we look up, we need to compute one, we first check the table. If it is already there, we look it up, otherwise we compute it and store it. But since we know there is a table and we know what the table structure is, basically it's all entries of the form I comma j, we can also see if we can fill up this table iteratively by just examining the subproblems in terms of their dependencies. So in general, a value depends on things to its left and below. So if there are no dependencies, it must have nothing to its left and nothing below, and there is only one such point, namely 0, 0. So this is the only point which is the base case which has nothing to its left and nothing below, so its value is directly given. So we start from here. So remember that the base value at 0, 0 is 1. Okay. And now, once we have done this, okay, it turns out, we remember the row dependency, it said I comma 0 is I minus 1 comma 0. So we can fill up this because this has only one dependency which is known now. So in this way, I can fill up the entire row and say that all along this row, there's only one path, namely the path that starts going right and keeps going right. Now, we can go up and see that this thing is also known because it also depends only on the value below it. And once that is known, then these two are known, so I can add them up. Remember, the sum of the value at any position is just the value to its left plus the value to its bottom. And now I start to get some non-trivial values. And in this way, I can fill up this table row by row, and at each point when I come to something, I will get the fact that the dependencies are known. So the next row looks like this, and the next row. Now we come to the row with holes. So for the row with holes, wherever we hit a hole, instead of writing the value that we would normally get by adding its left and bottom neighbor, we deliberately put a 0 because that means that no path is actually allowed to propagate through that hole. So now when we come to the next row, the holes will automatically block the paths coming from the wrong direction. So here, for instance, we have only 6 paths coming from the left because we have no paths coming from below. Similarly, we have 26 paths coming from the left and no paths coming from below. So this is how our inductive definition neatly allows us to deal with holes. And from that inductive definition, we recognize the dependency structure and we imagined a memo table. And now we are filling up this memo table row by row so that at every point when we reach an ij value, its dependent values are already known. So we can continue doing this row by row, and eventually we find that there are 1363 paths which avoid these two. So we could also do the same thing in a different way. Instead of doing the bottom row, we can do the left column. And the same logic says that we can go all the way up, then we can start in the second column, go all the way up, and do this column by column, and not unexpectedly, you should get the same answer. There is a third way to do this. Okay? So once we have 1 at 0, 0, then we can fill both the first element above it and the first element to its right. So we can do this diagonal. Now notice that any diagonal value like this one has both its entries, right? So this has only one entry. So I can now fill up this diagonal. So I can go one more diagonal. Then I can go one more diagonal. So we can also fill up this thing diagonal by diagonal. So the dependency structure may not require us to fill it in a particular way. We might have very different ways to fill it up. All we want to do is systematically fill up this table in an iterative fashion, not recursively. We don't want to call f of ij and then look at f of I minus 1j. We want to directly say when we reach ij, we have the values we need. But the values we need could come in multiple different orders. So we could have done it row wise, we could have done it column wise, and here you see we can do it diagonally. But it doesn't matter so long as we actually get all the values that we need. So one small point, so we have said that we can use memoization or we can use dynamic programming. One of the advantages of using dynamic programming is it avoids this recursive call. So recursion we had mentioned earlier also in some earlier lecture comes with a price, because whenever you make a recursive call, you have to suspend a computation, store some values, restore those values. So there is a kind of administrative cost with recursion. So actually, though it looks like only a single operation when we call fib of n minus 1 or fib of n minus 2, there is actually a cost involved with suspending this operation, going there and coming back. So saving on recursion is one important reason to move from memoization to dynamic programming. But what dynamic programming does is to evaluate every value regardless of whether it's going to be useful for the final answer or not. So in the grid pathing, there is one situation where we can illustrate this. Imagine that we have these obstacles placed exactly one step inside the boundary. So now if you want to reach this, it's very clear that I can only come all the way along the top row or all the way up the rightmost column. There's no other way I can reach there. So anything which is inside these positions, there is no way to go from here out. So there's no point in counting all these values. Okay. So we have this region which is in the shadow of these obstacles, which can never reach the final thing. So when we do memoization, when we come back and recursively explore, it will never ask us to come here because it will never pass these boundaries. On the other hand, our dynamic programming will blindly walk through everything. So it will do row by row, column by column, and it will eventually find the zeros, but it will fill the entire n by n grid. So in this case, how many will memoization do? It will do basically only the boundary. So it will do only order m plus n, right? So we have a memo table which has only a linear number of entries in terms of the rows and columns, and a dynamic programming entry which is quadratic. Okay, if both are n, it will be n square versus 2n. So this suggests that dynamic programming in this case is wastefully computing a vast number of entries. So n square is much larger than 2n, remember. Okay, so it will take us enormous amount of time to compute it if we just count the cost of the per entry. But the flip side is that each entry that we need to add to the memo table requires one recursive call. So the reality is that these recursive calls will typically cost you much more than the wastefulness of computing the entire table. So in general, even though you can analyze the problem and decide that memoization will result in many fewer new values being computed than dynamic programming, it is usually sound to just use dynamic programming as the default way to do the computation.